Okay, welcome back. We are on to lecture 3. Today we are talking about homogeneous equations. Very fancy, tough sounding name, but we will see that they're not so bad. All right, so first of all, what are they? So of course they are differential equations. So these are differential equations with some properties that tell us what they are. So that's how we classify them, and then we'll see how to solve them after that. So first of all, these are D's that can I'll say why I underline that a bunch in a second, can be written in the form where you have y prime or dy dx if you want on one side and all the x's and y's on the other. And because all the x's and y's are on the other side, you can think of that side as actually being a two variable function of x and y. But that's the fancy way of saying it. So this is really meaning that you can algebraically move x and y to one side, y prime to the other. And then because you only have x's and y's on one side, no derivatives, you can think of it as a two variable function of x and y, if you want to get very fancy. And the reason I emphasize can is because it doesn't have to already be like that. The point is you have to be able to do that. And then that's the first step into being a homogeneous equation. Okay. And so second, that's the first step. You also have to show that once you've moved everything algebraically to one side and you have a two variable function, you have to show that if I replace x and y with t times x and t times y, that nothing changes, meaning that it'll equal whatever was over there to start. But this is just a very fancy way of saying that. So meaning if you replace x with tx, y with ty, then what will happen is the t's will cancel. So that's what it means to be homogeneous. First, you write it like this, then you test this little condition here, and if it happens, then it's homogeneous. Okay, so then once you know it's homogeneous, then you'll see a little technique about how to solve it. But first, let's see an example. Okay, so let's show that this is homogeneous. So I first have to be able to separate the derivative from the variables, which I can by just dividing this x over. And so we're done. So this on the right side is a function of x and y. It's only got x's and y's in it. So the first condition is met. The second condition, all I have to do now is think about what this means. So this means I take my two variable function, I replace x with tx, I replace y with ty, and see what happens. So y becomes ty, x becomes tx, and then I'm checking to see if, when all is said and done, it just equals the same thing again, which it will because I can factor out this t on the top. The t's will cancel. So yes, I am back to where I started. So I'm homogeneous. Okay, so not so bad to test that it's homogeneous. Now, how do we solve it? Well, we're going to pull a little trick. So the interesting thing is, of course, when people develop the tricks, they don't just like magically come up with them, but what you see is the result of lots of hard work. So it seems more like a trick than a natural way to derive it, but that's okay. It's to help us save some time. All right, so we can use a little trick. And so what this trick will do is it'll turn a homogeneous equation, which is what we have, into a separable one. And why is that good? It's because we know how to solve these. We did that last time. So this trick is not really a trick for solving homogeneous equations. It's more a trick of turning one into a separable one, and then we know how to solve those. So let's see how this works. Okay. So it really is going to seem like a magic trick. All we're going to do is we are going to let y, we're going to do a substitution, equal x times some v, where v is another variable that depends on x, so it's a function of x secretly. But we're not like specifying, okay, v of x is some, we're not going to say like, oh, it's specifically some function. We're just saying it's a function of x. And if I make this substitution, everything will work out great. We can sort of see why we might want to use this, a substitution like this at least. If you think about this condition, you can see why this might be a good idea. This is really saying that if I have a variable on each one, I can cancel it out. So it doesn't matter what the letters are called. So if I replace y with x, or sorry, yeah, replace y with xv, then I have something that sort of looks like this condition. And this is really saying I could cancel the t's, but now it's saying I could cancel the x's. So that's what we're going to do right now. Okay. So anyway, we'll do it when we need it. Okay, so then we're going to make that replacement. And then we're also going to replace dy dx with something else. But to see what it is, we're going to apply d dx to this little equation, this substitution that we're making, to see what happens. Okay, so what is the derivative of y with respect to x? Well, it's just dy dx. That's the definition of the derivative of y with respect to x. What about on the right side? Well, it's a product of two things involving x, two functions of x. So I have to use the product rule. So I take the derivative of the first one times the second one. I add, then I leave the first one there, and I take the derivative of the second one and multiply. And what's the derivative of x with respect to x? It's just 1. What's the derivative of a function of x with respect to x? Well, just by definition, it's dv dx, the same as why this guy was dy dx. Okay, so just to rewrite it one more time, dy dx is the same as v plus x dv dx. So we are going to, that says appy, how about apply? Okay, so what we're really going to do is we're going to use two substitutions. We're going to substitute this into our homogeneous equation, and we're going to substitute this into our homogeneous equation, and everything is going to magically, seemingly work out. So let's do that. So now plug these in to y prime equals f of x comma y. So let's do this in general and in our example. since we already have an example to work with to see how it's working. So, so our example is, I have to scroll back up because I forgot it. Here it is. We have this. Y prime equals y plus x over x. So let's see how this substitution works in general, and then also at the same time in this example. So what I'm doing is I'm making two substitutions. dy dx is going to become v, sorry, was it v? Yeah, v plus x dv dx, and I'm going to replace y with x times v. Okay, so that's that side. And then on the right, I'm replacing y prime, which is dy dx. So replacing it with v plus x dv over dx. And then I'm replacing y with x times v. Okay, so on the left here, we're now using this rule that if I have a homogeneous equation, it has this property where if I have a variable being multiplied to both inputs, both coordinates, then that variable will always cancel. And I'll get back the same thing without the variable. Well, this is the same thing, same setup, with different letters. So I can think of x as x times 1, and then I have x times v. So those x's are going to cancel according to this property that I have. I'm going to get a function of 1 and v now, and there's not going to be any x's left. And that's what should happen over here. Accordingly, it should be the same thing. So, and it does. So if I factor out that x on the top, I should get a function that only involves the variable v and the number 1, I guess, no x's. So that's exactly what happens. I just get v plus 1. So good. So in general, I should always have a function that doesn't have any x's left in it. And I do see that happening in this example. And now it's separable. So I can get all my v's to one side and all my x's to the other. So instead of x and y, it's x and v as my two variables. But that's okay, it still works the same. So in general, what can I do? Well, I can subtract that v over, and then I can multiply to get the dx up, but then I have to divide that x down, and then I can divide this whole thing underneath. And now I have a separable equation with v's on the left and x's on the right. So I should be able to do the same thing here in my specific example. So if I subtract the v's to the right, to start with, I just get a 1 there. And then if I now multiply the dx and divide the x there, then I should only have v's on the left, which I do. So now that it's separable, I can solve it just by integrating. So in general, it's going to be hard on the left to continue because I don't know the general integral of something that looks like this. But in a specific example, I can do it, well, hopefully. And then on the right, the integral of 1 over x is ln of x. So it's going to end up like that. So in general, we're going to just stop there. But on the right, we can continue. So in this specific example, the integral of v is v, and the integral of 1 over x is ln of x. Sorry, the integral of dv is v. So then, sorry, I gotta check 1 second. Okay. So then, oh yeah, plus C. So then am I done? Well, not really, because I want my solution to involve x's and y's, but I still have this extra variable v here. So what can I do next? So now I can replace v, because I know y equals x times v. That means v equals y over x. So I'm going to replace v with y over x. And then I'm going to multiply by x. And I'll have an explicit solution. And then that'll be it. So this is an explicit one parameter family of solutions. So if we just take a look back here, what this is saying is we actually have a formula for that we could possibly use to jump all the way to the end of solving a homogeneous equation, but I don't recommend doing that. I recommend doing this each time just to get used to it. So you do the substitution. Y equals xv and dy dx equals v plus x dv dx. So do this substitution once you're here, once you know it's homogeneous, and then work through it each time. Don't try to just jump to the end using the fact that there is a general formula for what will happen. Okay, so let's see one more example. These are kind of long, so I'm not going to do too many examples. And the only practice you have to do is doing the substitution, because after you do the substitution, it just becomes separable again. So there's no real point in doing too many examples. In terms of showing you examples, you should do plenty to practice, of course. Okay, so this one, I'll just already put it in the right form for you. And then we'll just test it real quick. Okay, so yes, it's already in the right form. We have that y prime is equal to a function of just x's and y's, great. And now we're gonna test if it is homogeneous by replacing y with ty, so this becomes ty to the fourth, and x with tx becomes tx to the fourth. This becomes tx, this becomes ty cubed, and what do you know? A t to the fourth will pop out from the top and the bottom, and you'll be left with exactly what you started with, so that's good. So those cancel, and this is just back to being this function again. It's two variable function, so yes. Okay, so it is homogeneous. So now let's solve it. So we'll replace y with xv, and then dy dx with I always have to recalculate it in my head each time, v plus x dv dx. That comes from the product rule again. Okay. So again, what I'm doing is I am just replacing it here. Okay, so y prime once again becomes v plus x dv dx. And then I guess I have to zoom out so I can actually see it. I'll zoom in again after. So y becomes xv to the fourth. Nothing happens to x. X is x. Y becomes xv. That one's to the third. Okay. So now, because math is so wonderful and consistent, I already know it's going to become separable. All right, so I can factor out an x to the fourth, and I can factor well, it just is there, x to the fourth v cubed. So good. Those x to the fourths cancel. And as predicted, the x's on the right will always cancel when it's homogeneous. And they do. So now it's separable. So you just separate, and now you're back to doing problems like last lecture. But it's already set up in the same way every time. So you're always going to subtract this v over first so that you can separate. Here, the best way to do is get a common denominator, and then it won't look so bad. So this becomes that, and then it works out okay. So this becomes v to the fourth minus 1 over v cubed. Wait, why did I change the plus 1 into a minus 1? Sorry, it's a plus 1 still. That's okay, no such thing as a mistake. Just a happy little accident. All right, from which to learn from. So then, now I can separate. I have to multiply v cubed up, divide v to the fourth plus 1 down. I have to get the dx up and then divide the x down. And now I can integrate. Now we have to remember a little bit more complicated integration techniques as we keep going. So to do this integral, you're going to need to remember u substitution. So this is a double substitution problem because I'm doing another substitution. So u is going to be the denominator. Du will then be 4v cubed dv. Then dv, I can solve for that, will be du over 4v cubed. And then I can continue. So different people do use substitution different ways, but it all amounts to the same thing. Okay, so that becomes u. dv becomes du over 4v cubed. On the right, I'm just going to get ln of x again plus c, so that'll always happen. If you notice, that happened last time too. That's just set up in the general method. You'll see that will always happen. Okay, but then the v, the left side, that will be different depending on the problem. You have to do different integrals for it. Okay, so the v cubes will cancel. You can bring out the 1/4. Then you can integrate 1 over u, becomes ln of u. And then you got to change it back into v's, and then you got to change it back into y's. So u was this, so now I'm going to change that back. And then I'm going to change v. So y equals xv, that means v must be y over x. So I will change that to that. And I'm going to leave it here as an implicit solution because it's sort of big and complicated. But you can simplify it more if you want. So for example, you could multiply by 4, and then that 4c will change into you can just change it back into a c. You can then use exponentials to try to get the logs out of the way, stuff like that. Okay, but that's going to be it for this video because the rest of the examples are very similar. They just depend on your ability to do this integral here. So whatever integral you get here, depending on how easy or hard it is, that's what affects the difficulty of these problems. Because these steps will always be the same. So you just have to get good at that step. Separating after doing the substitution, and then integrating is the hard part. Okay, so see you next time.